The very first question is a search question. You probably know about the Towers of Hanoi. If you don't, then please go and Google them. It's a single-player game for which you try to move the tower of 4 slices over here onto the right peg over here. You can use the middle peg, but the rules are you can only move one disk at a time, and it might never happen that a small disk sits below a larger disk. So the way to solve it is to move the disk over here, the second largest is to the right side, the small one over, and the third largest to the center, and so on. If you know it, you know what I'm talking about. If not, just Google it. So I would like to know what is the size of the state space of valid disk configurations in this puzzle. Please enter this here. I'd like to know whether the number of the disks on the left peg are an admissible heuristic if you use A* search. And I'd like to know what's the number of steps that an optimal solution will require to move all the disks from the left peg to the right peg. The answer to the first question is given by a simple algorithm. Suppose you place the largest disk first, which has 3 different locations, then the next disk on top of it, which is another 3 locations, the third disk and the fourth disk. Then for each disk you have 3 possibilities, and you have 4 disks, so it makes 3 to the 4th, that is 81. The disks on the left side are an admissible heuristic because it takes at least that many steps to move all the disks from the left side to the right side. And finally, the number of moves required is a little bit tricky, and you have to know the solution here. You will finally move the big disk once, but to move it to the right side, you previously moved the second largest disk to the center and then move it over to the right side, which is 2 motions for the second largest disk. For the third largest, you'll move it 4 times by the same logic, and the smallest is being moved 8 times. The total going to be 15. That's the same as 2 to the n minus 1 if n is the number of disks. So here's a Bayes network with 6 variables a, b, c, d, e, and f, and I'd like you to count parameters. If this was a binary Bayes network where each variable can take on 2 values, then a would require 1 independent parameters, and b another 1, and c would require 4 independent parameters, because there's 4 different ways a and b can come together and condition c. Now, in this question, I'd like to ask you, what happens if each node can assume 3 values, not just 2? So A can be A1, A2, A3, and C can be C1, C2, C3. For each node, specify the number of independent parameters required to state the conditional probability of that node. And I tell you, this is a tricky question. So for A, the correct answer is 2. I won't give you the other ones. And it's 2 because A can take 3 values, but it takes 2 independent parameters. The last one can be inferred from 1 minus the first 2. Please fill in the values for all the other variables. The answer for B is 2 again, same as A. It has 3 values, but 1 can be deducted from the other 2, so it's 3 minus 1 equals 2. C is more difficult. There's 9 possible combinations for A and B, and we multiply 9 by the possible outcomes of C, but we observe that we only need 2 for the outcomes and not 3 by the same logic that A and B had 2. So 9 times 2 equals 18. D is easier. There's 3 different conditioning values for D. And again, for each of those, we need 2 outcomes. The third one can be deducted, which makes it 6. E has 3 incoming arcs. 3 to the third is 27. For E itself, for each of these cases, we need 2 variables for the outcome, which makes 54. And finally, F is the same as D, which is 6. This is a true or false set of questions for machine learning. Suppose we've trained a machine learning model, and we found really good values for our parameters in our model. And now we're going to increase the noise that affects our data. What should we do to accommodate the increase of noise? Shall we increase k if we're using k nearest neighbor? True or false? Increase k if you're using the k-means algorithm? True or false? Increase k if you're using Laplacian smoothing? True or false? Use fewer particles if you're using particle filters? True or false? And use more data if available? True or false? Now with more noise, we need to increase k in k nearest neighbor because a small number of neighbors might be insufficient. So the answer here is true. We'd like to generalize over more data points. If we use k-means, we shouldn't increase the number of cluster centers. We were just happy with the number of cluster centers, and using more will make the situation worse. Therefore, the answer is false. In Laplacian smoothing, we should increase k because we smooth more, which will accommodate the problems introduced by additional noise. Of course, we should never use fewer particles in a particle filter. That's clearly false. And if more data is available, we should always use it, irrespective of the noise, but specifically if we have more noise, we should go to even more efforts to find more data. So this is absolutely true. So this is a planning question, and I apologize, it's a little bit hard to read. There's a lot of text here. And I ask you to consult the PDF document to read the text. Given the resources on the left over here, can we reach those 5 goals, A, B, C, D, E on the right side? And in looking at those, there's words like consume, which means the action eliminates the resource, whereas use means you have to have it, but you retain it after using it. Now initially, you know there's a couple of books, one by Now about planning, one about Sweben about scheduling, and one by Melville about whales. And there's also videos. Video 8 is about planning, and video 15 is about scheduling. These might be our in-class videos. That's your initial state. And your goal is that you, as a student, know about planning and you know about scheduling. So the question is, with certain resources that are available in the beginning and that differ from question to question, can you attain the state of knowing about planning and scheduling? Now there's 2 ways to know about a topic. One is to study it using a book, and one is to view it using a video. In both cases, the outcome is to know about the topic over here. Now, either one has a different precondition. In the book case, you have to have the book, and the book has to be about the topic you care about, in which case the action study lets you understand the book and you know about the topic. So for example, if you have a book about planning and study it, then you know about planning. In the view case, you have to have a video that's about the topic, and you have to have a certain bandwidth, which happens to be 2.5. If you don't have the bandwidth 2.5, you won't be able to view the video and you won't be able to know about the topic. That's the way the problem is set up. Now, books can be bought or borrowed. In the buying case, you consume $50. In the borrowing case, you have to have a privilege at the library that's at least 1. It might be larger, but it can't be lower than 1. And in either case, after doing this, you have the book, and you can now plug this into the study action, and you can read about it and study it and know the topic. So here are the questions. If your resource is that you have $50 and you have library privilege of 1, can you then attain the state of knowing about planning and scheduling? Secondly, suppose your resources is no dollars, but you have library privileges of 2. Can you attain the same state? Third, what about the same with library privileges of 1? Can you get here? Fourth, what about you have $40 and bandwidth of 3? Can you get here? And fifth, what about you have bandwidth of 2 and $95? Can you get here? Check all or any or none of those 5 questions that apply? The answer to the question is that the first 4 apply, but not the 5th. Let's go through those. With library privilege 1, you can borrow books. You will use the privilege, but you'll get it back. You won't consume it. And you can do this for the first book, the Schweben book, and the second book, the Now book, in which case you now have both books. And then you can go and study those books. They're about the correct topic, and finally you know what's going on. You won't even need the $50. With Library Privilege 2, you can do the same, which is even better than Library Privilege 1. And again, Library Privilege 1 is sufficient. You won't need any money to do what you're out to do. Now, without library privileges, you can try to buy a book, but $40 is not enough to buy the book. It costs you $50. So the only way to do this is to watch videos. It turns out there's a video about planning and a video about scheduling in your initial state. Both can be watched using a bandwidth of 2.5, and you have a bandwidth of 3 over here. So by doing both, and by observing that you don't consume the bandwidth, it still stays with you, you can watch them, and as a result, you know about planning and scheduling. The only thing that fails is the last one. With $95, you can buy 1 book, but not 2. So in 1 book, you can go and buy it, you own it, you have the book, and then you can study the book and be knowledgeable about a specific topic, but it's not enough to buy 2 books. Bandwidth 2 is not sufficient to watch a video, so this action over here won't get you there. So what you find in the last case, E, is that the dollar amount and the bandwidth are insufficient to make you knowledgeable about planning and scheduling at the same time. This is the only case that fails. This is a question about logic. We have 4 different statements. Pink is true. Pink or green is true. Pink and green is true. And not pink implies that green is true. Now, these statements could imply each other, and in this matrix over here, I like you to select each circle where an implication is necessarily true. It's always true. For example, if you believe that pink implies that pink or green is true, then mark the A implies B circle over here. If you believe that pink is true implies pink and green must be true, then mark the circle A implies C over here, and so on for the entire matrix. One hint, D looks complex, but it happens to be the same as one of the previous cases. So if you fill out the matrix for A to C first, and then copy the result over for D, it'll be easier than if you start thinking about D separately. And to find the equivalency of D, just write on the truth table of these different things over here, and observe that D is already represented among A to C. To answer this question, the very first thing we observe is that each statement implies itself. So we will draw every element on the man diagonal as true. We also observe that not pink implies green is the same as pink or green. If you do the truth table, you'll find that this is true either if green is true, which will be the case for B as well, or if pink is true, in which case the precondition to this implied will be false, and therefore the entire statement is true. So we can find out that B is exactly the same as D. With that in mind, we answer the question for A to C first. Pink clearly implies that pink or green is true. It doesn't imply that pink and green is true, so C is not open. But because B is equivalent to D, we also check over here. Pink or green doesn't imply pink, because green might be true. And doesn't imply pink and green, because green might be false. But it does imply D, because D is exactly the same as B. Pink and green implies pink. It also implies pink or green. And since B is the same as D, it implies D. And finally, for this one over here, we just copy over B. So we get this guy and this guy over here.